it's our great pleasure to host this virtual workshop on integrated sensing and communication, and in particular, information theoretical limit and signal processing techniques. So I am co-organizer Mari Kobayashi from Technical University of Munich, together with Hamdi and Franz from Technical University of Eindhoven, Netherlands, and Giuseppe Caire from Technical University of Berlin. So we are all here. And a very special thanks for Fan Liu and Shangguan Li and Yuan Hao Kui for technical support, in particular Zoom setup, as well as advisements. Thank you very much. And yeah, so since our workshop focused on partially information theory, we have prepared a few slides to explain why information theory is useful for integrated sensing and communication. So first of all, in general, fundamental limit can be characterized by using information theory, or although under sometimes oversimplified and restrictive assumptions, such as arbitrary long code word or IID source or memoryless channel. But still, these limits can provide insight into the performance gain we can gain with a practical integrated sensing and communication scheme, for example, compared to the conventional scheme which separates sensing and communication. So typically we use a performance metric for communication, for example, capacity and decoding error probability or error probability exponent, or for sensing, if you're interested in target detection error probability and its error exponent, or distortion for the parameter estimation. Yeah. So and in particular, we emphasize that the feedback information theory is very useful here, and it enables to design adaptive strategy. For example, for purely communication scenario, there are well-known adaptive strategy to improve the capacity or improve error probability performance. But this feedback can be, of course, used for other problems such as target search or active learning. Here, we listed a very short list of recent progress, both from information theoretical perspective and from signal processing. So first, our group has characterized optimal trade-off between state sensing and communication. So it was ISAC paper a few years ago, and there has been a follow-up work, and it will be one of the first speaker from by Michèle Wigger as the extension of this first point. And recent work from Hamdi and Franz Williams, they characterize also optimal trade-off between detection and communication. So it's a very recent work. And we have also other type of framework based on active learning applied for beam alignment and tracking. So this can be also enhanced by integrated sensing and communication. And of course, there are so many works from radar signal processing approach that we cannot list here. And we simply refer a few overview survey tutorial paper, and we listed just 2 paper here. Okay. So finally, I close my introduction by providing some challenge and open problem. So from information theoretical point of view, of course, fundamental limit under more relaxed and realistic assumption would be very interesting. For example, instead of IID source or state, we can try to think about non-IID or stationary or ergodic state, or think about replace the channel, memoryless channel with memory. So channel with temporal correlation, or also we can think about finite broad length code. And beyond probably detection and parameter estimation, we can also study fundamental limit of communication and recognition or classification. And also we can think about distributed scenario where you can collect information from different distributed nodes in the network to do estimation or tracking. And maybe most importantly, we want to also bridge the gap between these information theoretical model and signal processing techniques. So this is the end of my short presentation. And here is the schedule of our half-day workshop. So we have 6 excellent speakers from different areas. And each of 6 speakers, we have half an hour. So roughly a very brief introduction and talk of 20 to 25 minutes. And we want to dedicate roughly 5 minutes for Q&A session. So, and for Q&A session, probably you can post your question in ahead to us by using chat, and then Hamdi or I will correct few questions and try to unmute those who have questions to interact directly with speaker. Okay. So if there's no specific question, then we can start. So I just stop sharing my screen. And Michèle, you are here?
Yes, hello, can you hear me?
Yes, I hear you, and you are muted.
I'm unmuted, right?
Yes, you are unmuted. So maybe you can start sharing screen while I'm give a short.
I think it says host disabled participant screen sharing. So it's as you wish. I think you have the slides. Otherwise, you need to give me permission to share the screen.
Ah. Hamdi, can you give?
Maybe we can make Michèle a co-host, and that would, I think.
Yeah, maybe.
Okay.
Can you do this?
Yes.
And we have to do the same for all the speaker then.
For some reason, I can't find you.
Oh.
Hamdi, your voice is a bit low there. I think you should get closer to your microphone.
So can you, Hamdi, give the permission? Ah, okay. Now, Michèle, you are able to normally share the screen now. Good.
Perfect.
So Michèle is a professor at Telecom Paris Tech, France, and she's an excellent expert on network information theory. In particular, she has a very famous work on broadcast channel with feedback. And recently, she has been working on different problems such as distributed detection, distributed caching, and computing system. And today, she represents her recent work on fundamental limit of integrated sensing and communication. So please, Michèle, I will mute. Go ahead.
So thank you very much. Thank you very much for the invitation and the introduction. It's a great pleasure, of course, to give this talk. And the results I'm going to present are based on collaborations with my PhD student, Merasa Ahmadipour, and Giuseppe Caire and Mariko Bayashi. Yes, so because I'm the first, wait, let me see. Yeah, since I'm the first talk of this workshop, maybe I should give a quick motivation, just a brief one. Most of you, I think, already know. So traditional approach is to have like one hardware for the communication. For example, here we have the example of autonomous driving. So we have car communicating with maybe other cars or base stations. And then we have a second hardware for the radar, because the autonomously driving car, of course, also needs to sense for obstacles or maybe for the speed of other cars and so on. And so traditionally we have two hardwares, two systems, maybe working on different time slots on different bandwidth. And so we call this approach usually the resource splitting approach. So now a few years already, people actually started about integrating the two systems. And I think the motivation is pretty clear, because in the radar, you actually interested in the backscattered signals. So you send a signal and then you're interested in the backscattered signals to obtain information about distances and so on. So the forward signal in this sense does not have lots of useful meaning. It certainly does not contain lots of information. So the idea is now to use the signal sent for communication, which bears information that you want to communicate. So here we model it by the two messages for the two receivers. And so you want to use the backscattered signals of the communication signals for the radar. And so maybe here to add, so this is an integrated system. So what to add here is that we will only have one waveform that now has to do both tasks. So it has to serve for the communication task, and it has to serve for the radar task. And this is what leads to this, this problem of designing synergistic waveforms. So waveforms or channel inputs, they're good both for sensing and communications. And we might have hear more about this today in the workshop. That's a very active research field. On the other hand, so people who are more from the communications field, they know that actually these backgathered signals, which we call feedback, they can also be used not only for radar applications, but to improve the performance of the communication, especially in the multi-user scenarios on which I want to focus on this talk. So I'll be focusing on a broadcast scenario where we have one transmitter and two receivers, or many receivers as here on the picture. And I'll also talk about the dual channel. So where you have like two or more transmitters communicating with a single receiver. And in fact, for this later setup where we have more transmitters, there's another interesting thing going on, because as I already said, so the waveform we are going to emit, the transmitter emits, bears information about the data we want to communicate. But as we're going to see, what you should also do is actually, you should also code information that is useful for sensing on your transmit signals if you have multiple transmitters. And I think this is a new feature, at least in the information theoretic integrated communication and sensing literature. Okay, so this actually, so I hope I could motivate a bit the problem. So now let me give you or explain you the information theoretic model. So the information theoretic model has been introduced by Kobayashi, Kairi, and Kramer. So here on the slide, you see the broadcast version thereof. It has been introduced on the point-to-point channel, but because here we focus on broadcast channel, I want to introduce it on the broadcast model. So let me walk quickly and slowly through the model because it's a bit complicated. So you see the things, boxes and arrows related to communication are in red, and more related to estimations or sensing are in blue. And then we have magenta for the combination. So the things that serve for both tasks. Okay, so we have two receivers. Of course, they're only interested in the communications. They're not involved in the radar application. So each of them wants to learn a message based on their channel outputs, Y1 and Y2. Okay, the encoder knows the messages and sends them to these receivers. So this is the communication part. Then the transmitter so the transmitter participates, of course, in both in the estimation and the channel coding. So besides sending messages, it also wants to produce the estimate of the state. So here the state of the system is it can be the environment, it can be the distances between users, it can be obstacles, or maybe fadings, things like this. So the state here is modeled by state sequence Sn, and it influences the environment. So here the environment is going to influence the channel. So here we have a channel input xi. This represents the transmitted waveform, the xi, okay? So this really serves both purposes. So it needs to do channel coding, and also it needs to be good for the radar application. And then the channel, so from the input to the two outputs and to the backscattered signals, so the Z is the backscattered signals, information theory models it just by an abstract transition law. We call it channel transition law. So you can take any conditional probability distribution that takes an input, so the input waveform, the state, this is the environment, and then based on that produces channel outputs and backscattered signals. Okay, so I just want to emphasize that with this you can model many things. You can, for example, model fading channels. So here you have the S here, that is the fading at the receiver, or you can also model when S represents, for example, the distance, then maybe the fading is simply something related to the distance, but not a function. So you can have a more general version. So you can model any kind of things. And for the generalized feedback, you can choose any distribution you want, pz given y1, y2, x, and s. So for example, you could use some, again, the distance times the input signal plus some different noise different than at the receivers, okay? So maybe what I want to say is like the model is very general. And so the idea of information theory is to provide general answers, but then you have to, if you want to analyze a specific system, you'll have to plug in specific values for this channel loss. And I also want to mention that often people in communications, they like channel state information at the receiver. Of course, this is also included in this model because you can simply add the states at the as part of the output signals. Okay, so this is the model, and so that's communication model, sensing model, and in terms of sensing performance, we use, as Mario also said, we use average distortion measures. So here we have a distortion function, and then we want that this average distortion, so this is the state, and this is the reconstruction at the transmitter, so this could be the estimate of the distance of a car, should not be too large. And here the D popular functions, of course, are binary Hamming functions, squared error functions, or other things that you want. And in particular, you can also have functions that only take, that are not really, don't really measure the distance between SI and SI hat, but only functions of these variables. And finally, we can also treat vector states where each of the two, for example, if you want to have like the distance to each of the two receivers, so you have a S1 for receiver 1 and the S2 for receiver 2, in which case you would need multiple distortion functions. Okay, so with this, I hope I could motivate the model. And the performance measure we're interested in is the capacity distortion trade-off for the capacity distortion region, which is simply the set of all triples of rates. So this is the rate of message 1, rate of message 2, and then the distortion of the estimator. And you want that the probabilities of error of the receivers tend to 0 as the block length tends to infinity. And moreover, the estimation performances, average per estimation performances do not exceed D. So if we look, okay, so this is we're interested in the capacity distortion region. So as we said, we have two problems, we have a communication and the sensing problem. So as long as we only have one transmitter, for example, in the point-to-point setup, or when we have two receivers, then actually the optimal estimators is not so difficult to obtain. So the optimal estimator at the transmitter, so the transmitter, it knows, of course, its own channel inputs. It knows the generalized feedback, so the backscattered signals it observes. And then the best estimate to produce is that each symbol, so you take, these are two sequences, n-length sequences, and you take a per symbol estimator. And for each symbol, you simply take the best estimate that is going to reduce your expected distortion. So in other words, what is interesting here is that the estimator only depends on the statistics of the input signal, so on your waveform, I'm sorry, on your waveform and the backscattered signals, but not how you create this waveform, so how it encodes the information. So in this sense, as long as you have one transmitter, you actually can decouple the communication problem and the sensing problem, because the sensing only depends on the waveform. So they're not completely decoupled, because the sensing performance depends on the XN statistics, which of course is an important thing in a communication scenario, but in a communication system, but basically any communication systems with the same input waveform will have the same sensing performance. In other words, so the trade-off between communication and sensing really comes from the design of the waveform for the communications problem. Okay, so now that we decoupled still somehow the problem of sensing and communication on a broadcast channel, we have to understand how do we want to communicate on a broadcast channel with generalized feedback. And as Mario already said, so this was actually a very active, this was quite kind of an active research area, maybe 10 and 20, 30 years ago. And so we have results that we can use. So here is the model just without the sensing. And for this model, so we just have the communication part, we know feedback does not increase if the BCs are degraded. So for example, if this is simply a processed version of this signal here. Okay. In contrast, if we have a non-degraded channel, which is most often the case, then actually feedback can improve capacity. We don't know the exact capacity, but achievable schemes have been used. So what we can use now for the joint communication and sensing problem, we can use one of these schemes and then see on which input distribution or which waveform we should choose so as to obtain a good sensing performance. Okay, so maybe let me just give, if I have time, yes, let me give a quick idea on how we want to code on this broadcast channel with feedback. So the idea is to use a block Markov strategy. So we do communication in blocks, and in each block, we're going to send new data to the two receivers. And also we actually look back to the previous block, and the transmitter with its feedback signal and its input tries to find out whether there's a common noise component, there's something information about the noise in the previous, or about the channel in the previous block that could be useful for both receivers at the same time. And if this is the case, it will send it in the next block, and the receivers will use this information to improve their decoding performance in the previous block. And the idea here is that if you send information is useful for both receivers at the same time, you get a better performance than if you just have to send message M1 to one and message M2 to the other. Okay, so this is the idea, and this idea has been exploited and the coding scheme has been proposed, and we can simply use this to obtain a coding scheme for the joint communication and sensing problem. I'm not writing the performance here because it's a bit complicated to put on a slide, but the paper is on archive, so you can verify the achievable region we get. So for general broadcast channels, we have an achievable region, a feasible region for the joint communication and sensing problem, and we also have regions which we know are not possible. So we know certain triples we cannot get them. Okay, they don't match in general. For degraded broadcast channels, in contrast, because feedback does not increase the capacity, so the problem was easier and we could solve the problem. We gave the capacity distortion regions. So here, for people who are familiar with the area, you find the expressions for the degraded broadcast channel R1 and R2. And the only thing you have to add is that you take the optimal estimator and you only allow to choose inputs, so waveforms, such that this optimal estimator obtains an estimation performance that is not too large. Okay, so this brings me to the next sample. So here I plotted this, capacity distortion region for a simple example. So we have a fading outputs. So we have two states. We have a double state that can be correlated. And in fact, they're degraded in this example. So we have the first fading out. So Y1 is S1 times X and Y2 is S2 times X. And the receiver gets both feedback, and we assume that we have perfect channel state information at the receivers. And so this red line shows the capacity distortion region, or at least the boundary thereof. So everything that's underneath this red curve is achievable. Okay, so you see, for example, here, if R1 is small, then you can get a large R2 because there is a trade-off between the two rates. And moreover, the distortion, so here, the distortion here is small and here it's large. So if we allow for a small distortion, then actually we cannot have lots of rates. If you allow for a large distortion, here we can have lots of rates. Okay, and the point is because on this channel, if the transmitter wants to learn the state SK, it should always send X equal to 1, right? So input X1 is good for radar, but also input, and therefore gives you distortion 0. But input X1, if you only send a 1, then you cannot communicate, and that's why you get a rate equal to 0. Okay, and so if you allow for a bit worse sensing performance, you can get higher rates, and the more rate you have on R1, the less rate you get on R2. And here we also showed in 2 resource splitting approaches. So if you just have 2 systems, one that is optimized for communication and the other one for sensing, and then you time share between the 2, or you take you split the bandwidth between the 2. And you see it's highly suboptimal. They only get this, so the boundary is given by this, this green and blue dotted lines. Okay, so I would like to conclude, I think maybe I have like 5 minutes or so for on the multiple access channels. So here, this is still a bit work in progress, so we should be soon have something on archive. So the idea is here, okay, so here we have 2 transmitters and only 1 receiver. And so it's a similar model as before. Now, of course, we have 2 states. One, each transmitter wants to sense a different state. They could be the same. It can be anything, any joint law, PS1, S2. And then we have the backscattered signal, the different signals at the 2 transmitters. And I think, so here there are various remarks I would like to make. The first one is maybe if you go on communication. So we know feedback here is useful on communication. And one way to see that is actually it creates new communication paths, because if you look at it, now there's a communication path from transmitter 1 to receiver 2, because from input from transmitter 1, you go through the channel to the feedback backscattered signal at transmitter 2. So now suddenly transmitter 1 and transmitter 2 can communicate to each other. And this has been known in information theory to be useful in the sense, okay, it goes back to Cover and Liang, or I think Gardner and Wolf actually. So you send information, so each transmitter can send information, the other transmitter can decode it through via its feedback link, and in the next block, so again do a block Markov coding, they can jointly cooperate in sending both messages together. So both, because now in the previous block, each transmitter learned the other guy's message, and so now on they can actually cooperatively communicate them, which is more efficient. So here, now that we have a sensing problem also, we are going to use this alternative communication path. We can also use it to send sensing information, right? Because, okay, so here we have the path from transmitter 1 to transmitter 2. And so imagine in a scenario where you have, so you want to sense another car, and at the moment you want to sense it's actually closer to transmitter 1. And so transmitter 1 will be able to better estimate the distance, you'll get a better backscattered signal, but later on, this information is also useful for transmitter 2. So in that case, transmitter 2 really wants to know the distance of this car who is closer to transmitter 1. And here, transmitter 1 can use its inputs also to send information about this distance to transmitter 2. So I call this coding for sensing, because here the coding is not, the communication is not for data communication, but to improve the sensing performance. And here you also see, because you can transmit information relevant for the sensing, that the simple sensing we had with one transmitter, where you simply apply a symbol-wise estimator on the channel inputs and feedback outputs, is suboptimal now, because you also want to take into account the information you got from the other transmitter. Okay, yes. So maybe here I just have a toy example. So now, I have a toy example that illustrates that, just like so I gave the practical motivation before. This is really like an information theoretic example to prove that we need this new idea and it helps in improving systems. A previous joint sensing communication system for the Mac that did not code for sensing. So this is an example, toy example. We have the Y just has a fading S2 times X2. So it does not depend neither on S1 or X1. Actually, S1 here doesn't exist. Transmitter 2 gets S2, so the distance to this other car. Transmitter 1 can observe it perfectly. And moreover, transmitter 2, here it's assumed has a dedicated link, communication link from transmitter 1 to transmitter 2. In this case, a simple strategy, if you want to have zero distortion at transmitter 2, so that transmitter 2 can perfectly get S2, transmitter 1 is simply going to repeat its feedback signal. So it's going to send the state from S2 from the previous block, and this way transmitter 2 gets the state from the previous block. Okay, and obviously you cannot get the same sensing performance if transmitter 1 does not help transmitter 2 in this sensing task. Okay, so maybe a little more technical, and I think this is almost the end of my talk. More technical, especially for those who are familiar with the previous coding schemes for the Mac with generalized feedback. So we used the scheme proposed by Willems in '83 and adapted it to include also the coding for the sensing. So it uses block Markov coding, so communication is in blocks, and backwards decoding, so you start decoding from the last block. And we already, as I said before, so we have a first layer in each block where you actually both transmitters send the same message. And this is because they repeat the message in the previous, that they exchanged in the previous block, okay? That allows them to cooperate. But now, so in each block, they also have to send the current message. So in the next block, they can use it for cooperation. But now, so this U1 code word has to be decoded at the other transmitter. This one is decoded at the other transmitter. And here we can plug in compression information, which are called the J's, which are simply information about the state information I obtained from the previous block. So in the previous block, I obtained information about the state interest that is of interest to the other user, and I'm going to compress it and describe it using in this U1 code. So everything was already there. We just had to add in these messages. Okay, so I think this brings me to the end of my talk. So here on the Mac part, so we have this new idea of coding for sensing. We incorporated in Willems' scheme, and this gave us a better and improved achievable region compared to the state of the art. I didn't show it here. It's again complicated. It will be soon be on archive. However, the general problem, I also have to tell the general problem is widely open, because these feedback problems are actually, even without sending, still very open even after decades of research. Okay, this brings me to the summary of my presentation. So what I wanted to do, I wanted to explain the information theoretic framework for integrated sensing and communication, which was actually proposed by Kobayashi, Kairi, and Kramer. And so I want to point out that as long as you have a single transmitter, the sensing is kind of easy, at least in this information theoretic framework. So the sensing is easy because it's a symbol-wise estimator. It, however, leads to the trade-off between the rates, different rates and distortions, because it depends on the common waveform. However, for the multiple transmitters, we kind of also need coding for sensing. And this leads to what I maybe call a fully integrated coding for sensing and communications, because now the coding screen really have to integrate both tasks at the same time. And future interesting research directions. So I think one thing that I noted here is what Mari also mentioned, is the assumption that we have IID states and memoryless channels. And I apologize if this wasn't clear enough. So in our setup, the states are IID and the channels are memoryless, in the sense that the time I outputs only depend on the time I inputs and states. And with this, actually, I would like to conclude my talk. Thank you very much for your attention.
Thank you very much, Michelle. Does someone, the audience, have question?
Hi, Michelle.
Hi. Hi, Shlomo.
Good to see you. Tell me, Michelle, when with the state information, when you say degraded broadcast channel, actually the realization of the state can change the degradedness.
Yes.
So, you know, so
Yes.
the statistics, what is exactly how you define the degradedness with the state, meaning that degradedness, who is degraded is kept?
No, actually, I think so. Okay, so in the paper, what we did, we assumed state information at the receiver. Okay.
Yeah.
So receiver 1 knows S1 and receiver 2 knows S2.
Yes.
And in that case, so you want the Y, so you need to have the S1 here and the S2. You're correct. Yeah. But I think if you don't, because you see for the ray constraints, you don't really care. Okay, if you do without side information at the receivers, for the ray constraints, you don't care what the transmitter is going to estimate. So basically here, the steps for the converse are exactly the same as for the,
but you have side information at the receiver. So it's degraded when Y is both the receive signal and states.
Yes, when you have state information at the receiver, certainly you need to include S1 here and S2 here.
Here,
if receiver one knows S1
that's
and
exactly
receiver
my
knows S2.
question.
Yes,
because
yes.
You know, without even
but here actually, yeah. So in this talk, I assume there's no state information at the receiver, but you are certainly correct. Yes.
I think.
Michelle, so the results are all for, as you told at the end, for IID states. Eh?
Yes.
So did you think about an alternative definition? So what should we do? So in a practical situation, a radar situation, yeah, the states are not IID, I would say.
Yeah.
Or can you argue, or can you do some signal processing such that the states become IID, or do you have another concept of state statistics in mind, like the entropy of the state is small, for example? Did you think about this?
I have to admit, I did not think in, I did not think in, or at least I didn't come to any interesting conclusion. I would guess actually I think the situation changes, right? I don't think that you can do just signal processing and then assume. I think the coding is going to change now if you have states in the system.
Yeah. Well, it's something that bothers us.
Yes.
So we assume that the state is constant. Eh?
Yes.
And
So
you assume that the state is IID, but what something in between, what would be nice will lead to results. That's a question for us.
But because I'm just thinking, like, because there are, like, for just like the channel with feedback, people have looked at channels with memory, right? Like, for example, Chaim with he has all kinds of Chaim Permuter. He has all kinds of memory.
Yeah.
And I think maybe like coding techniques, like I think a first step would be like to use his coding techniques, which I think are different than from what we are using in these IID states.
Okay. Well, thank you.